Kıymetli hocalarım, kıymetli arkadaşlar, sevgili öğrenciler. Bugün biz TÜBİTAK olarak çok değer verdiğimiz fen lisemizin siz kıymetli öğrencileriyle bir arada olmaktan ve böyle bir sizlere yönelik bilimsel etkinlik kapsamında bir güzel bölüm daha gerçekleştirmek üzere bir araya gelmiş bulunmaktayız. Ben de bu vesileyle sizlere hitap etme şansı bulduğum için çok mutluyum ve hepinizi sevgiyle selamlıyorum. Hasan Mandal Başkanımızın sizlere çok selamları var. Kendisi bir son anda çıkan bir program nedeniyle yetişemedi. Ben onun adına sizleri selamlıyorum. Bilindiği üzere bilimsel gelişim sürecinde yeni fikirlerin fevkalade önemi vardır. Yeni, çığır açan fikirler bilimsel gelişimin itici gücüdür. Bazen uzun yıllar boyunca iyi bilinen ve değer verilen fikirlerden vazgeçmek de bilimsel gelişim sürecinin bir parçası oluyor. Hatta bu şekilde yeni açılımlara da vesile oluyor. Günümüzde bilimin sınırlarındaki çalışmalar oldukça sıcak, bugünle alakalı olarak, kaotik ve fikirsel olarak gürültülü alanlarda gerçekleştirilmektedir. Burada bir yandan geniş kabul gören fikirlerin gücünden yararlanırken, diğer taraftan bu fikirlerin sorgulanması ve bazı fikirlerden vazgeçme olasılığı tartışılıyor. Ayrıca çağdaş bilimin sınırları tamamen yeni ve çok çeşitli, birbiriyle yarışan fakat doğrulanmamış fikirlerle doludur. Bugün bu kapsamda çok heyecan verici bir konuşma dinleyeceğiz. Bugünlerde Temel Bilimler Araştırma Enstitümüzü ziyaret eden dünyaca ünlü bilim insanı, Amerika'daki Kaliforniya Teknoloji Enstitüsü'nden Profesör Anton Kapustin bu konuşmayı özellikle sizler için hazırladı. Kendisine çok teşekkür ediyoruz. Profesör Kapustin, ısı ve elektrik birbirine benziyorlar mı başlıklı bir konuşma yapacak. Yüzyıllar boyunca iyi biliniyor ki ısı sıcak cisimlerden soğuk cisimlere doğru akar. Tabii ki sizler bunu çok iyi biliyorsunuz, gözlemliyorsunuz. Yaklaşık 200 yıl önce ünlü bilim insanı Fourier ısı akımının matematiksel yasasını ortaya koydu. Isı akımı sıcaklık farkıyla orantılıdır. Bu çok önemli bir yasa. Fourier yasası her ne kadar deneylerle uyumlu da olsa doğanın temel işleyişiyle ne kadar uyumludur? Bir başka deyişle bu yasa ne kadar geneldir? Bildiğiniz gibi yasalar genel kavramdır ve bu genel kavramın, bu yasaların aksi gösterilmediği sürece bu yasa geçerliliğini korur. Herhangi bir ispata gerek yoktur. Tabii sıcaklıkları aynı olan cisimler arasında, hani dedik ki yüksek sıcaklıktan düşük sıcaklığa akar. Fakat sıcaklıkları aynı olan cisimler aracılığıyla da arasında da bu ısı aktarımı mümkün müdür? Bu önemli bir soru. Tabii yine yaklaşık 200 yıl önce Ohm, hepinizin bildiği gibi elektriğin ısıya benzer olduğunu tespit etti, keşfetti. Nasıl ısı yüksek sıcaklıktan düşük sıcaklıktaki, yani sıcak cisimlerden soğuk cisimlere akıyor, elektrik de aynı şekilde yüksek elektrik potansiyeline sahip cisimlerden düşük elektrik potansiyeline sahip cisimlere doğru akar. Bu da ilgili yasanın temelini oluşturuyor. Isı ve elektrik birbirine benziyor. Fakat bu benzerlik nereye kadar? Bu da çok önemli bir soru. İlerleyen zamanlarda tabii süper iletkenliğin keşfiyle Ohm yasasının evrensel olmadığı ortaya çıktı. Bazen elektrik potansiyel her yerde aynı olsa da yine akabilir. Bu durum ısı için de geçerli olabilir mi? Yani bu ne demek? Sıcaklıkları aynıysa bir ısı transferi mümkün olabilir mi? Benzerlikle. Yarı iletken diyotlar tabii yine bugün günümüzün bir parçası. Peki ısı diyotları yapılabilir mi? Bunlar önemli konular. Tabii tüm bu konuları Profesör Kapustin'den dinleyeceğiz. Bu konuşma İngilizce olarak gerçekleştirilecek. Bu nedenle ben de İngilizce devam edeceğim. Dear Professor Kapustin, dear teachers, dear friends, dear students, a very warm hello to everyone. Today we came together to have another wonderful episode of our inspiring scientific activities for TÜBİTAK Science High School students, and it's my tremendous pleasure to welcome all of you for this special event. As it's known, Advances in science involve new ideas. New groundbreaking ideas are the driving force for scientific advances. Sometimes it turns out that scientific advances also involve giving up on cherished old ideas. In addition, the frontiers of modern science are full of entirely new and competing, but unconfirmed new ideas. Today, in this concept, we'll have a very exciting public talk. The world-famous scientist, Professor Kapustin from the California Institute of Technology, Caltech, who is visiting TÜBİTAK Research Institute for Fundamental Sciences, has kindly agreed to prepare this talk, especially for you. We thank him very much for this, and Professor Kapustin will give a great talk on heat and electricity. Are they alike? Professor Kapustin is the Earl Anthony Professor of Theoretical Physics at the California Institute of Technology. His research interests lie in quantum theory and its application to particle physics and condensed matter theory. Professor Kapustin obtained his Bachelor of Science degree in physics from Moscow State University in 1993. He received his PhD in physics at the California Institute of Technology in 1997 under the supervision of Jan Prescott. Professor Kapustin has made several groundbreaking contributions to dualities and other aspects of quantum field theories, in particular topological field theories and supersymmetric gauge theories. With Edward Witten, he discovered deep connections between the S-duality of supersymmetric gauge theories and geometric Lagrange correspondence. In recent years, Professor Kapustin has focused on mathematical structures in classification schemes of topological field theories and symmetry-protected topological phases. At this point, I want to thank Professor Kapustin once again for joining us and invite him to begin his talk. Professor.
Thank you for this very nice introduction. I'm excited to give a talk here. I'm also a bit nervous because I never gave talk to high school students before. It's first attempt. So let's hope it's all right. So I chose that subject, which is on one hand rather elementary, on the other hand touches on some unresolved questions in theoretical physics and even on some current research I'm doing. So let's see. All right. So here is something really elementary. We'll learn. Namely the heat conduction. So when you have two objects, hot and cold, heat always flows from hot to cold. So and actually it cannot flow in the opposite direction. There's something called the second law of thermodynamics, which one of its formulations is that heat never flows from cold objects to a hot one by itself. You can make it do that, but it won't do it by itself. Now, here's a question which people don't usually ask. What about the object of the same temperature? Can heat flow from between two objects with exactly the same temperature? Okay, let's see. So, this is a mathematical law of heat conduction, which again is very familiar. It's known as Fourier's law. So suppose we have two objects, let's call them A and B, which have two different temperatures, TA and TB. And A is bigger than TA is bigger than TB. Now, if you connect them somehow, then the heat will start flowing from A to B. How? Well, how fast? Well, the flow of heat is described by this Fourier's law, which says that the rate of heat flow is proportional to the difference of temperatures. The coefficient is called the thermal or heat conductance. Now, this law actually was proposed not by Fourier, who was a mathematician, but by Isaac Newton. Well, as usual, pretty standard thing that in science, laws usually misnamed and named after their own person. That's another example. And here, the reason is that, Isaac Newton just proposed this law, and then mathematician Fourier wrote a book in 1822, which developed a whole mathematical theory based on this law. By now, Fourier's law, we know it works very well. It's the basis for a lot of engineering, but actually, we still don't know why it works so well. That is, in some cases, we can derive it, but in most we don't understand why it always works. Now, about the same time, actually, 2 years later, Georg Simon Ohm, a German physicist, decided to study electric conduction. Now, he didn't have many resources. He was stuck in actually in high school as a high school teacher, and there was basically no lab, so he had to buy everything on his own. But nevertheless, he managed to do some research, and he studied how the flow of electricity, that is electric current, from one object to another, depends on electric potentials of the two objects. So he found that the electric current is proportional to the difference of electric potentials. We call them VA and VB because electric potential also known as voltage. So VA is the voltage on A, and VB is voltage on B. So if there is no difference of voltage, then the current doesn't flow. If there is some, then it flows from A to B. And the coefficient here, sigma, is called the conductance of this bridge, electric conductance. So it's very similar to Fourier's law. So actually, it's interesting how Ohm in 1825 discovered this law. Well, he wasn't a theorist. He was doing he actually was pretty good at theory too, but he discovered it experimentally with very little resources. So how did he do that? Well, voltage is looks the way this law looks like. Well, voltage analogous to temperature. The temperature is easy to measure, and voltage is not very easy to measure. At that time, nobody even knew exactly what voltage is. So how does it work? Well, he need to measure two things: current and voltage. Current was easier. Just 5 years before that, a guy named Ørsted discovered that electric current deflects, rotates a magnetized needle, a compass needle. So it was a brand new discovery. It was actually the first discovery that connected electricity and magnetism. So, and then immediately people, really the next year after the discovery, actually even less than that, people realized you can use this discovery to measure the strength of the current. So, well, you just wind your wire around the magnetized needle, which there, you get this device called galvanometer. If the current is strong, then this little magnetized needle rotates a lot. If it's weak, it rotates little. Also, you can see which way it rotates. So very, very simple, very useful device. Well, how does it measure the voltage difference or this potential? That's something rather invisible. So at that time, people didn't talk about voltage, but they said it's like pressure of electric fluid, something like that. So the analogy here is that you have a wire, it's like a pipe, and electricity is some sort of electric fluid. And to pump electricity through a wire, you need some pressure difference. Just like if you want to pump water through a pipe, you need the pressure to be bigger on one end. So, okay, so how do we measure this invisible pressure of the invisible electric fluid? Well, here is another thing which happened. The same year that Fourier published his book on heat, another German physicist named Seebeck found a way to predict electric current by using heat. Actually, he found that you can produce electric current by heating a contact between two different metals. So specifically, he used bismuth and copper. The disc made a disc with bismuth and copper wire, and it connected. The copper wire is connected to the disc both on the top and on the bottom. And if you heat one of the contacts or maybe cool it, then electric current starts flowing through the circuit. If you heat it, the current flows one way. If you cool it, then it flows the other way. So actually, it's a funny story how he discovered it. At first, he thought you don't need to heat anything; just need to connect bismuth to copper. Maybe the current will flow. And then he looked at it; it seems to work. But then he realized the reason it worked is because he used his own finger to press one of the copper ends of the copper wire to the bismuth. Only then it worked. If he used like a stick to press it, it didn't work. But he realized the heat that does it, not the. It wouldn't flow without this difference in temperature to the top and the bottom. So then once he realized that, he had some crazy theory about why this happened. Doesn't matter. The point is that Ohm learned about this discovery, which is now known as thermocouple, and essentially used this as a battery with variable voltage. You can easily change the temperature difference, and this way you can regulate how much voltage this sort of battery thermocouple produces. And then you can check how, and then to measure voltage, essentially measure voltage by measuring temperature. And then you can measure current using galvanometer, and then you plot one against the other, and you see there's a straight line. That's Ohm's law. Nowadays, of course, Ohm's law is something you learn early on. It's very basic. Every electrician knows about Ohm's law. But when Ohm published a book about this, the review was like, "You're crazy. Nobody should read this book. It's just nuts. It doesn't make any sense." Well, it took like 30 years for people to realize that Ohm actually got it right. And some engineers actually learned. Thomas Edison, actually, who discovered the light bulb, actually never even learned Ohm's law, even though he worked like 50 years later. So he just did everything by trial and error. Anyway, so if you look at this Fourier's law and Ohm's law, they're very similar. So in both cases, flow of something is proportional to the difference of something. So flow of heat proportional to the difference of temperatures, flow of electric charge proportional to the difference of voltages. And also, by the way, both coefficients are positive. They cannot be negative, because they can be prohibited by second law from the end. So heat always flows from hot to cold, and electricity flows from higher potential to lower potential. Okay, but is it just an accident, or is something more deeper here? Is there some deeper analogy? Now, the interesting thing is that Ohm's law is actually, now we know it's not universal. Sometimes it works, sometimes it doesn't. So, what are two important exceptions where it doesn't work? First of all, diodes, semiconductor diodes. So electricity flows more easily in one direction than in the other direction. This is extremely important. So this fact is actually what underlies basically all electronics. So the fact that you can have a symmetric, non-symmetric conduction. What I want to say is that this sigma, this electric conductance, actually might depend on the voltage difference very strongly. Another discovery is that there's some materials called superconductors, where this electric conductivity is actually infinite. Well, I'll explain later what it means, but basically it means that the electric current can flow even when there is no voltage difference. Okay, so is there something similar for heat? That turns out to be rather interesting and not a very simple question. So, well, let me talk about a little bit about possibility for heat diodes. So, electrons they carry both electric charge and heat. On the other hand, if you look at so to make the clean statement, let's look at insulators instead. In insulators, there are phonons, electrons that don't really move. So, and in insulators, heat is carried by phonons, which are quanta of crystal vibrations. And there is a whole name for an area of physics which studies how to control the flow of these phonons, called phononics. It's by analogy with electronics. Now, electronics is very useful, but phononics so far, well, more to be in this area of research. Nobody cannot go to a phononics store and buy phononics iPhones or something like that. So why is that? Well, it's not easy to control heat the way you control electricity. For example, it turned out very difficult to construct to build heat diodes so that heat would flow much easier one way than the other way. So why is that? Well, in this case, actually, the analogy does not work very well. So electrons have a repulsion, which actually very long range. So electrons repel. That fact is actually crucial for the way diodes work. If you look in engineering books, they explain how diodes work, and at some point you'll see you take into account that electrons repel. It wouldn't work without that. Now, phonons, of course, do not repel or actually interact at all, apart from each other. So that part doesn't work. And people who try to come up with designs for heat diodes use some totally different ideas. So heat diodes, even when they're built, will not work the same way that electronic diodes will. Okay, so that actually doesn't work. Now let's look at another thing, but where maybe there is more analogy: superconductivity. So, so about 100 years later, after Ohm, a Dutch physicist, Kamerlingh Onnes, managed to liquefy helium, make helium liquid, and when he decided to study conduction at this low temperature, he discovered that mercury actually becomes infinitely conductive. So it has infinite electric conductivity when temperature goes below 4.2 kelvin. Very surprising thing. He actually got the Nobel Prize for it. Now we know that actually all metals become superconducting at low temperature. Well, if that happens to electric conductivity, what about heat conductivity? Can heat conductivity become infinite? So let's see. Well, let's think about what this means. Okay. So let's write first of all Ohm's law differently. Let's divide by sigma. So you see that, and then take sigma to infinite. Well, what to learn from this is that there is no difference of voltage between A and B if sigma is infinite. Well, it's kind of funny thing. So now you learned that there's no voltage difference, but what about electric current? What determines electric current? This equation doesn't say anything about it. And actually, first question you can ask, okay, if the voltage is the same, so that doesn't mean you can have electric current from A to B without any voltage drop, even in equilibrium. Well, actually, this pretty famous physicist Felix Bloch argued as early as 1933 that in equilibrium you cannot have electric current, no matter what. It can be some exotic, can be very complicated thing. Yeah, please. Okay. So, okay, so that's a very important statement, which actually not very well known even to physicists. So there's no, if you have equilibrium, there's definitely no electric current. But you can still have maybe current, even though if there's no voltage difference. But you need to drive the system out of equilibrium somehow. But actually, interestingly, analogous statement, analogous to this one, analogous statement for heat was only proved 2 years ago in my work with my graduate student, with my postdoc at MIT. We showed that actually, similarly, if you have equilibrium, you cannot have a heat current. So I don't know why it took so long to realize that there's an analogous statement for heat, but maybe because the arguments to prove this is actually quite different from Bloch's arguments. But that shows that at least here the analogy works out. But that still doesn't answer the question. Okay, can heat be superconducting? Okay, let's talk a little, think about well, to discuss a little more what it means to be superconducting in the electric case. There's something called Josephson effect, which I'd like to discuss. So what is the Josephson effect? Well, actually two different Josephson effects, one called DC effect, the other one AC. I'll discuss DC effect. So in a superconductor, you have, well, not all electrons, but many electrons, microscopic number, condense and form Cooper pairs, which are they're all in the same state. So somehow superconductor is a macroscopic quantum object. And quantum mechanics says when you have a state, then it's described by complex number. And in this case, this complex number is not something about microscopic or some particle, but actually it's about the whole piece of superconductor because macroscopic number of electrons are in the same state. So there's some complex number, which is just a property of your piece of material. We call it psi. So the absolute value of this complex number is actually locked to something. But the phase here is arbitrary. It can be anything from 0 to 2 pi. So a normal piece of material doesn't have this parameter, but the superconductor does. So you have this extra parameter there. Now in equilibrium, so as I said, it's fixed, but phi can vary. So the reason you can have a current without voltage drop is because suppose you have two pieces of superconductor on this insulating bridge. So this absolute value of the size are fixed, but the phases, they're just chosen by whatever, and they can be different. So it might just happen the phase of this side here is different from the phase there. And if it's different, it means that the two pieces are not in equilibrium, even though there is no voltage difference between left and right. And then when this happens, Cooper pairs, they just go from left to, well, they of course go both ways, but when these phi's are different, there's no reason for the flow from left to right and from right to left to be cancelled. So in general, however, just current from some direction. So if these two phases are not aligned. And this current is there even without any voltage difference. And it's a current which is non-dissipative, which means that non-dissipative, which means that it's doesn't produce entropy, it doesn't increase entropy. Okay, now we can finally ask ourselves, what is the what will it mean for some material to be heat superconductor? So a heat superconductor would also have some number analogous to this phi. Let's call it tau. And when there are two pieces of this heat superconductor with different values of this tau, they would not be in equilibrium. And then if you connect them, then the heat would flow from one of them to the other, even though the temperature is exactly the same. So that nobody ever seen this happen, but theoretically there's nothing wrong with that. So at first I thought something must be wrong with the situation, like maybe it contradicts the second law of thermodynamics, and the laws of thermodynamics are sacred. But then with some work I realized that there's nothing wrong with it. It could happen theoretically. Whether it happens in real life, I don't know. I have spent some time thinking about that, still don't know. So so that's an unsolved problem, but hopefully, well, maybe one of you will solve it. So, or maybe me, if I'm lucky. So let me just say that I actually, by coincidence, I actually wrote a popular science book on the subject of electricity, which is only published this year, specifically for high school students. So, and some of the illustrations were taken from there. So, I discuss all this. Well, not all this, but I discuss the history of electricity and magnetism. And actually, it's an illustration in this book that attract attention. That some experiments, well, demonstration in the early 19th century, when people tried to use batteries to revive dead people. It didn't work, as you probably know. Still, interesting event. So actually, that's what apparently the Frankenstein's monster story is based on. So the successful attempts to revive people with electricity. Okay, so now I'll take questions.
Thank you, Professor, for this very interesting talk. So, floor is open for your questions. Just raise your hand and. Okay. Yep. Wait for the microphone.
Wait a second, microphone.
Like why do all metals become superconductors under like temperatures of 4.2 Kelvin?
No, not necessarily at that time. At some time.
Like why do they?
So well, it has been a matter of a lot of research, but basically, a metal turns out is unstable. So if you read zero temperature, there are no metals, strictly speaking. So a metal is a state of matter which is only stable for some sufficiently high temperature. That's what's been realized fairly recently. But anyway, the point is that electrons in a metal, they like to pair up and form these Cooper pairs. If temperature is non-zero, it might destroy this. But if the temperature is zero, they have to do this pairing thing. So at which temperature this pairing, this attraction between electrons wins, because they actually attract. At which temperatures attraction wins over temperature, that depends on the metal, but they all become superconductors, especially low temperature.
Thank you. in the Josephson effect for electrodynamics, how would one describe a system with a complex number, and how does one drive it? Does it make use of the Fourier transform or something other than that?
Well, yeah, so a complex number is basically this pairs of electrons. You can imagine that a pair of electrons is some wave function. And well, this wave function in principle could vary across your piece of material, but when you're in equilibrium, it has to be constant. All electrons have the same wave function, so they all have exactly the same numbers. You can just say it's a property of material. How do you drive it? Well, just as usual, you just turn on some electromagnetic field, electromagnetic field to drive that. Okay.
Thank you. If there is heat conductors, isn't it breaking the thermodynamic rules of the?
No, it doesn't break the second law. That is, usually when you have heat induction, that increases entropy, which is consistent, which is normal situation, right? But you can also have an energy flow, which does not increase entropy in principle. Nothing wrong with that. Second law doesn't prohibit you from not increasing entropy. It only prohibits you from decreasing entropy. But when it doesn't increase, nothing wrong with that. It's just that, let's say in superconductors, that actually does work. You have these currents which don't increase entropy. So similarly here, one can imagine that could be a transfer of energy without increasing entropy.
Does Bose-Einstein condensation have any relevance to this topic?
Well, Bose-Einstein condensation is I could have used the example of superfluidity instead of superconductivity to make the analogy. Yeah, it's just that electric conduction is somehow more intuitive. But in Bose-Einstein condensation is basically superconductivity, but not for electric charge, but for atoms of some material like helium or something. So I could have used that as an example. Yeah.
Thank you.
I think you tell everything about the likeness between heat and electricity, but how would you define the main difference between heat and electricity?
Well, there's one very important difference. Well, that's one very important, most obvious thing that electric charge is quantized. Everything comes in quantum. Like all electric charges are integral multiples of electrons charge. Of course, with energy, it's not at all like this. So that's one big difference.
Thank you.
Is there no more questions?
When does your book which season of the year? You said the lightning in a bottle.
Yes.
When we will be able to read your book?
Not sure. But most likely pretty soon, because the book is essentially finished.
right? It will be in English, right? Are there any preparation for translation for any other?
No, it's all in English.
Any more questions about science, for example, for career, to the professor, how he decided to become a scientist, etc. Those kind of things that you are curious about it, not necessarily science, but maybe some professional related.
It's okay. I'm not that interested.
Well, maybe you can say any advice for the students, how they if they want to become like follow your career.
Well, I think it's first of all also fun. I don't regret it for a second. It's exciting. I try to. But when your job is actually what you love the most, is great. So second, well, when I was in high school, I just mostly self-studied. So I didn't actually learn anything from my physics class in school. So I just read books on my own and just solved lots and lots of physics problems on my own. I remember was in last grade in high school, I picked a book on elementary particles. I remember the name is Halden and Martin. And I just solved every single problem from beginning to the end. And, also, physics Olympiads is a lot of fun, so I participated in some. So this is, yeah, used to be this Russian magazine, Quantum, which is available online now. You can find complete archives. So it was published in Russian, but then it started being published in English too. So for several years, so you can find these English issues online. And every issue has problems in physics and math. And it's again, for a couple of years, maybe several years, I just solved every physics problem from the magazines. Really recommend. Plus, they have great articles about physics and math in English. So it's something I would recommend doing.
So how many of you are preparing for or more interested in physics? Any hands? More enthusiastic hands? Okay. Okay, good. Any more questions? No? Do you have a question over there?
Biraz yüksek kaldırın elinizi. Çok yazık değil.
Ha. Orada bir soru. Evet. Orada şey yapar mısın? Oraya verir miyim? Ha. Var mı kaldı? Tamam. Ha. Arkadaş.
I want to ask something about careers. Is physics a good choice for career? I want to ask because in the physics it's all theory.
No, not at all. Not at all theory, with lots of applications. So first of all, there are people who work on theory like I do, but even I like sometimes look for things which might be useful for engineering. So so physics by itself, or applied physics in particular, can be quite useful. You definitely will not be without a job if you do physics. And it's a simple law of supply and demand. Just not that many people are capable of learning physics. And if you know something which almost nobody else knows how to do, that's very valuable. So plus it's a lot of, well, I'm not saying you should go into physics. Lots of other things which are fun you can do. Like, I have a student, former student, who is doing mathematical biology now, for example. So that's also great. But he's actually using his training as a physicist to study embryology of the evolution. So physics training is good in any case. Yeah, so he got his degree in physics, but then he switched to biology. I forgot to say, even more of my former students are on Wall Street, making a lot of money in finance. One of my former classmates at Caltech, has his own investment company, doing very well.
Do you have any achievement in Olympiad?
Sorry?
Do you have any? Do you have any achievement in Olympiads?
Which one?
Achievement.
Physics Olympiads.
Oh, well, I got first prize in Moscow Physics Olympiad, but once I got to the Soviet Union level, I messed up the experimental part completely. In theory, I did great, but in experimental, I just did hopeless.
So, what was the story about you started the physics Olympiads?
Well, I didn't take it very seriously. It's just that I was solving these problems from the Quantum magazine, which is the kind of Olympiad style problems. I thought, okay, I'll try also Olympiads in Moscow, you know, just local ones. Actually, I think my teacher said, okay, you're doing well in physics, why don't you go to Olympiad? She sent me to all kinds of Olympiad. I remember doing an Olympiad in economics. I don't know anything about economics. She told me to go, I went, okay. But in physics, I was excited, so I decided to participate and go to the all Russian level. It's actually not that, it's interesting mostly because I meet other people who are also interested in physics, science. That's the only main reason to do it. Because in my school, I guess nobody else cared in my class. So once I got to this competition, there's lots of other people also excited about science. I guess that shouldn't be a problem here.
Currently, which topic are you working on?
Several actually. So
Has an exam?
like one of them is well, first I'm trying to understand something about this heat superconductors, but it's kind of, I don't have any concrete ideas, just still thinking about it. There's another big project which is about classifying all possible quantum phases of matter that is phases of zero temperature. That's like a big project. Well, all of them is probably too complicated, but there is some subset of these phases called short-range entangled, which basically have little entanglement in different parts of the system. So this is, well, there's some ideas how to do it. There's actually a conjecture which I made a few years ago about what the answer is, but I still don't know how to prove it. So work on that.
What should I read or learn about as a ninth grader or high schooler if I want to study superconductor in the future?
Well, that's a rather advanced topic. Probably start with something simpler, right? So, which is, well, superconductor is a quantum phenomenon. So you need to first of all learn quantum mechanics, which by itself is pretty advanced. So first you need to learn something like classical mechanics and statistical mechanics, dynamics. So there are some books on this. So, for example, there are several books written by Landau and Pythagorean, which are called, I think, Physics for Everyone. It's a like 4 or 5 volume series for actually high school students. The first 3 of them is actually quite good. The last one not that great. the first three cover all the basics. It goes all the way to like thermodynamics and statistical mechanics. So we'll start there. And after that, we can like try to look at college textbooks.
How many students do you have and from which nation?
I mean, graduate students.
It doesn't matter. I just
I mean, students like Caltech has very international crowd, but I don't usually interact with most of them. So it's I know students I work with in my group. There are like usually 3 or 4 students every year. And
generally where they are
from everywhere. Right now, I have also postdocs. So I have a guy from Poland, from China, from Russia, and a postdoc from Belgium.
Thanks.
Yeah. No more questions. Let's thank the professor for this very interesting and inspiring talk. And with your new book, I guess you will be inspiring many students all around the world. So we wish you great success in that. Thank you very much for coming and for doing very interesting talk. Very good. Thank you. Tamam. Thank you. Teşekkürler katılımınız için hepinize. Hem farklı enstitülerimizde, merkezlerimizde bu tür seminerler oluyor aslında. Şimdi bana bu da bir fikir verdi. Biz de yani her hafta işte seminerlerimiz var, davet ettiğimiz. Bu noktada sizleri de aslında tutacağız. Çok teşekkürler hepinize geldiğiniz için. Başarılar diliyorum. Yeni yıl.
Gençler